Hello students, welcome back again. Now we are entering to the last and very important section in which we will discuss questions asked in IIT-JEE, and these questions are based on the very important concepts involved in simple harmonic motion. In this question, these questions are based on restoring force condition, time period, energy involved and these. So let's begin the topic. Let's begin with some important question asked in IIT-JEE exams. Now the first question is a mass m shown in the figure oscillates in a simple harmonic motion with amplitude A. The amplitude of the point P is. So we have to find out the amplitude of point P, that it's just a joint between two springs K1 and K2 and mass m. So we know that this arrangement is actually a series phenomena. So force experienced by first spring should be equal to force experienced by second. That should be equal to K1 x1 should be equal to K2 x2. Equation 1. Second, the net amplitude is just the sum of extension produced in both the spring, that is x1 plus x2, that is equal to A. Because already we are given in the question, the amplitude A is just the sum of displacement like extension or compression. Here is a case of extension. So K1 x1, K2 x2. So from this relation we will get K1 upon K2, that should be equal to x2 upon x1. So we would like to put the value of x1 and x2 from here, that A is equal to x1 plus x2 is actually K1 into x1 upon K2. So from this relation we are getting A is equal to K1 plus K2 into x1 upon K2. So finally we are getting the value of extension produced in the first. Means if this part is extended by x1, this point will elongate also. Means this point P is also displaced by position x1. So we have to find the value of x1, that is what? K2 into A upon K1 plus A2. So option D is the correct choice. We have to mind here the arrangement as a spring and force experienced by both the spring will be same. K1 x1 is equal to K2 x2, and the net amplitude is just sum of the extension produced in spring 1 plus extension produced in spring 2, and in this way we put the main equation, we put these values in main equation and get the answer option D as main choice. Now we will proceed question 2. In question 2, a simple pendulum has time period T1. A simple pendulum. So we know that simple pendulum T is equal to 2 pi under root of L upon G, case 1. It is having time period. The point of suspension is now moved upward according to the dimension or displacement y equal to k square. We are given the value of displacement as y equal to kt square, where the value of k is 1 meter per second square. Where y is the vertical displacement, we have to find out the time t2 and then the ratio t1 upon t2 whole square. So we know that t2 is equal to 2 pi under root L upon acceleration effective or g effective. That should be equal to 2 pi under root of L upon g plus e. Now the question is, how can we find out the value of acceleration? Easily we are given the relation y is equal to kt square. On differentiating this displacement dy upon dt, we are getting twice of k into t, and again differentiating we are getting acceleration, that is equal to d2y upon dt square, and that is equal to 2k. On substituting the value of k as given in the data, now that is equal to 2 meter per second square, and we will substitute this value in the second equation and then find the ratio, that is t1 upon t2 is equal to under root of g plus a effective upon g, and that is squaring both sides. We are getting t1 square upon t2 square equal to g plus a upon g, and that is equal to, considering g as 10 plus 2 upon 10, so we are getting the ratio is equal to 212 by 10, that is equal to 6 by 5, and so option A is the main choice. So what we did in this question, it is just a case of time period of a simple pendulum. T is equal to 2 pi L upon G, case 1. Now, question is, the point of suspension is now moved upward according to the relation y equal to kt square. If the displacement in the system is y equal to kt square, so differentiating displacement to get acceleration, because Due to this acceleration, time period would be affected as T2 equal to under root of L upon G effective. We will proceed. T1 upon T2 is equal to under root of G plus A upon G, squaring both sides. We are getting 10 plus 2 by 2, that is equal to 6 by 5, and option A is the correct choice. Now, question 3. In question 3, one end of a long metallic wire of length L is tied to the ceiling. The other end is tied to a massless spring or spring constant K. A mass M hangs freely from the free end of the spring. The area of the cross section and the Young's modulus of the wire are A and Y respectively. If the mass is slightly pulled down and released, it will oscillate with a time period T. And what is that value? We are given 4 options. T2, T is equal to pi under root M upon K, T equal to 2 pi M upon K effective as YAK upon YA plus KL, and T equal to 2 pi MYK upon KL, and D option is 2 pi. First of all, we can try this question dimensional. We can check the dimension check. We can have a dimension check, or we can avoid any two options, or one or two. Means first, if we do the dimension check, definitely one option would be out. Now, for the correct solution, how we should proceed? Here there are two systems. One system is metallic wire that is connected with a spring. On giving small jerk, the displacement produced in the system is sum of strain like delta x1 in the metallic part plus delta x2 in the spring part. So we will write the solution part as, in this question, we know that we want to know the restoring force, that should be equal to M into restoring acceleration. So restoring force is actually K effective into the displacement produced in the system. Now the question is, how can we find out the displacement produced in the system? So delta x is actually delta x produced in the metallic part wire plus delta x produced in the spring. So we know that in case of Young's modulus concept, Young's modulus Y is equal to stress upon strain. Stress is actually force upon area divided by delta x by net elongation x. So in this way we can get delta x is equal to force by area into this part and multiply by x elongation. Now in case of a spring, so we will get delta x is equal to force upon K, because force is same as it's a series phenomena, so force in the spring upon the spring constant K plus F into x upon A into y from this part. Now this is the value of delta x. Finally we have to find out the K effective from this part. So K effective multiplied by F upon K plus Fx upon A into y. Or in other term we can say that K effective, 1 upon K effective is actually 1 upon K plus x upon A into y. Original length of the rod is x is equal to L. So we can say that is 1 upon K plus L upon A into y. So we want to know the time period. So T is equal to 2 pi M upon K effective. So calculating the value of K from here and substituting over here in the main equation, so we will get T is equal to 2 pi under root M upon K effective is as KAY upon AY plus K into L, and that support option B the main choice. So what we did in this question? Actually, when we have a series phenomena either of two spring or either system of two SHM of two system, here is a rod like wire of initial length L1 connected in series with a spring of length whatever it is at initial. Now on giving small jerk F, on giving a small jerk to the system, so we are getting net force, and in the system is actually force is equal to mass into restoring acceleration, that should be equal to K into delta x. So delta x is the extension produced, that is just sum of delta x1 plus delta x2. So delta x1 is the extension is part 1, that is equal to stress, that can be calculated from the part Young's modulus is equal to stress upon strain, stress is equal to force upon area, strain is delta x by x. Actually x is the length L, So we can take this part over here, f into L upon A into y. So we know that as it is a series phenomena, so f upon k plus fx per se, taking f common from this part, so we can get 1 upon k plus fl upon A into y. So this is actually the net spring constant that can be taken as 1 upon k effective is equal to 1 upon k plus x upon ay. X is actually the length L part. So we got the value of k effective. We know that when we have a series phenomena, we want to note its time period. So it would be equal to 2 pi under root m upon k effective. So calculating the value of k effective from the main equation, substituting in the main equation, we will get t equal to 2 pi under root m upon k upon ay plus kl, and finally that would be equal to 2 pi under root of ay plus kl into m divided by kay, and that support option B as the main choice. Now we will switch to the next question. In this question we are given a simple pendulum has a time period t equal to 2 seconds in air. Now if the whole system or arrangement is placed in a non-viscous liquid whose density is 1 by 2 times, so density of the liquid is 1 by 2 times of density of the metallic ball, the time period of the liquid will be. So it is actually the case of SHM in a non-viscous liquid. So we know that case 1, time period T1 when it is equal to 2 pi under root L upon G effective. So as we are given, that is equal to 2 seconds. Equation 1. Part 2. T2 is equal to 2 pi under root L upon G effective when it is dipped in a viscous of density rho L, that is equal to half of density of. So according to the principle of viscosity, we know that according to principle of buoyancy, we will know that effective weight m into G effective will be equal to net weight minus thrust. So actually we are getting the value of G dash will be equal to G into 1 minus metallic, this rho L upon metallic part. So we are getting this part, that is 2 pi under root of L upon G effective, and it should be equal to 2 pi under root L upon G into 1 minus rho L upon rho metallic part. So from this relation we get T1 upon T2 square is equal to under root of G upon G into 1 minus 1 by 2. When we solve this mathematical equation, T1 upon T2, that is equal to G would be cancelled out, we are getting under root 1 by 2. So we want to know the value of T2, that T2 is equal to root 2 times of this value, 2 pi is also there, so it would be equal to root 2 times of the initial time, because we are given T1 as 2 second, so we are getting 2 root 2 second. So means that support option C as the choice in this part. So means what we did in this question, actually when we dip any object of mass m and density rho in a liquid having density rho L lesser than that value, so due to buoyancy or thrust, its gravity, its weight would be different. So G effective equal to G minus 1 upon density of liquid where it is placed upon density of metallic ball. So carrying these relations, we are getting T1 upon T2 is equal to 1 by 2, and finally we get option C is the main part. So as option A should be the main part, because it is just a reverse phenomena from this part, G upon 1 by 2 from this, option C will be the main part, main choice over here, and we will proceed according to this. Now question 5. In question 5, two bodies M and N of equal masses are suspended from two separate massless spring or spring constant K1 and K2. Two bodies that is connected with two equal masses are suspended from two separate massless spring of spring constant K1 and K2. It is actually M and spring constant K1 and K2. Massless spring of spring constant K1 respectively. If the two bodies oscillates vertically such that their maximum velocities are equal, so maximum velocities of one should be equal to maximum velocities of M and N, both of these. The ratio of the amplitude we have to find. So we know that maximum velocity is equal to amplitude A1 or m into omega m should be equal to amplitude of n into angular velocity of n. And we know that omega is actually equal to k by m from this part. Masses are also given. So we have to find the ratio of amplitude. So ratio of am upon an can be taken as omega n upon omega m. So that is equal to the ratio of omega n. Omega n is actually kn upon mass n divided by under root of km upon mass of an of this value. So we are given separate mass of, so two bodies m upon equal masses. So masses are same. So finally we are getting relation am upon an should be equal to under root of kn upon km. And their values are k1 and k2. So that support option D. So we can say under root k1 upon k2. So in this question, actually we need to find out maximum velocity, that should be equal to maximum displacement, that is amplitude multiplied by angular frequency. So am omega m is equal to an omega n. A is amplitude, omega angular frequency. Angular frequency in terms of spring constant k and mass is given as under root k by m. So we will take value from that part and put in the relationship of ratios of two amplitudes a1 upon a2 or am upon an, that is equal to under root of kn upon km, and so finally we get k1 upon k2 whole under root as the main choice. Hence option D is the main answer of this question. Ask IITians brings you a very good opportunity to paste your questions regarding the subject. What you need to do? First of all, select www.askiitians.com, then choose Ask a Question link. After that, you will reflect a discussion board where you can post your questions. After that, you need to go for Select Category. If you want to paste a questions regarding electrostatic, choose the concerned link, then type your question. After typing the question, select Get Answer. Then you will find the answer of your question within 24 to 48 hours. As in this part, we discuss IIT-JEE questions asked on different topics involved in simple harmonic motion. I hope you enjoying this part. So I would like to summarize complete theory involved in simple harmonic motion. As we discuss about oscillations and its type, like overdamping, damping, underdamp, and free oscillation, artificial oscillation. Then we switch to the kinematics of simple harmonic motion. We learn what is simple harmonic motion. After that, we discussed about displacement, velocity, and acceleration mechanism involved in simple harmonic motion. After that, we discussed the graphical analysis involved. Then we calculated energy, kinetic energy, potential energy, and total energy. Also, their graphs, dependent function of time and dependent function of displacement. Then we switch to systems of SHM. In system of SHM, we calculated time period of simple pendulum, spring mass system, and hydrometry, and although LC oscillations. Along with this, we discussed phasor and phasor relationship. So we calculated phase relationship of acceleration, velocity, displacement, and also the energies. And finally, we discussed the superposition principle involved when two simple harmonic vibrations are in same phase or out of phase, or they are in same dimension or opposite dimension or perpendicular to each other. And then we switch to the previous equations as we discussed in this part. For more, I hope you enjoyed the session. I hope you enjoyed the lectures. So for more video lectures, stay tuned with the Ask IITians videos. Thank you and God bless you.